In the previous module, we have seen that the polynomials over a field share many properties with the integers. Especially, you can remember that the irreducible polynomials over a field behave like the prime numbers in the ring of all integers. Recall that every non-constant polynomial over a field can be expressed uniquely as a product of irreducible polynomials, and there are many other important roles of the irreducible polynomials. But in the previous module, we have omitted the most important question, how to test the irreducibility of a polynomial over a field. The basic goal of this module is to introduce some results on irreducibility of polynomials over a field. But at the beginning, I share with you that till now we do not have very efficient results on testing of irreducibility. Anyway, let us see the results on irreducibility. Here we will discuss three results on the irreducibility of polynomials, and our main emphasis is on the polynomials over the field Q of all rational numbers. First of all, I will give a result which can be applied only to the polynomials of degree 2 or 3, and it is not applicable for the polynomials of degree greater than 3. And then we discuss a result on the irreducibility of polynomials over Q, which actually an application of the first result. And the third result is the celebrated irreducibility criterion due to Eisenstein. And finally, I will demonstrate an application of the irreducible polynomials to construct finite fields. So, our first result is irreducibility of polynomials of degree either 2 or 3. Suppose f x is a polynomial over a field f, and degree of f x is either 2 or 3. Then f x is reducible over f if and only if f x has a root in f. Here we will prove the result only for the polynomials of degree 3, and the proof for the polynomials of degree 2 is similar. So, assume degree of f x equal to 3, and this is a necessary and sufficient result. First, we assume that f x has a root in f, say a. Then by the factorization theorem, it follows that x minus a is a factor of f x. That is, we will have some polynomial q x over f such that f x equal to x minus a into q x. Since f is a field, it has no divisors of 0, and so the degree of the product x minus a into q x becomes equal to the sum of their individual degrees, and from which it follows that degree of q x is equal to 2. Thus, f x is expressed as a product of two polynomials. Both are of degree less than the degree of f x, and hence f x is reducible over f. For the converse part, assume that f x is reducible over f. Then f x can be expressed as a product of two polynomials having degrees less than degree of f x, that is degree of g x and degree of h x must be less than 3. So, either degree of g x equal to 1 and degree of h x equal to 2, or degree of g x equal to 2 and degree of h x equal to 1. Assume that degree g x equal to 1 and degree h x equal to 2. So, if degree g x equal to 1, then g x can be written as a x plus b, where a b are in f. Since degree of g x is 1, so the leading term a must be non-zero, and as we have assumed f a field, so a inverse exists, and it is easy to check that minus a inverse b is a root of g x. Thus, we get a root minus a inverse b of f x in f, and hence the result follows. This result can be applied very efficiently, in particular to the polynomials which are considered over a finite field, because a finite field contains finitely many elements. So, whether it has a root or not in this field can be checked in a finitely many steps. To demonstrate, let us consider a polynomial f x equal to x square plus x plus 1 over z2. z2 has only two elements, 0 and 1, and you note that neither 0 nor 1 is a root of f x, and since f x is a polynomial of degree 2, so by the above result it follows that f x is irreducible over z2. In the last section of this module, I will use this polynomial to construct a finite field of order 4. Now, I will show that the above result is applicable only to the polynomials of degree 2 or 3. The result is not applicable to the polynomials having degree greater than 3. It is very simple to note that f x equal to x square plus 1 and x square plus 2 is a polynomial over Q, but has no roots in Q. Still, it is not irreducible, because it becomes a product of two polynomials having degree less than 4, that is having degree less than the degree of g x. Though this result is beautiful and efficient for the polynomials of degree 2 and 3, still main drawback of this result is that it works efficiently to the polynomials considered over a finite field. Otherwise, if we consider a polynomial over an infinite field, then it is not so easy to check that the polynomial has no root in this field. We have tried to overcome this difficulty, though not very successfully. Actually, our technique is to reduce the polynomial over z into a polynomial over some finite field Zp. How to reduce? Suppose fx is a polynomial of degree n having coefficients ai over z. Denote, I mean associate a polynomial, say f bar x to fx in this way, where box a0, box a1, box an all are integers modulo m. And you can check that the mapping psi z to zm defined by psi a goes to box a is a ring homomorphism, and from which it follows that psi star zx to zmx given by psi star fx equal to f bar x is also a ring homomorphism. Now, to prove the main theorem, we need a lemma named after the celebrated mathematician Gauss. Gauss lemma tells us that if a polynomial fx over z has a factorization over q, then it will have a proper factorization over z also. Formally, if fx equal to gx into hx over q, where degree gx and degree hx are less than degree fx, then there are gx and hx over z such that degree gx equal to degree small gx and degree hx is equal to degree of small hx, and also we have fx equal to gx into hx. To prove this, first note that if capital Gx and capital Hx are two polynomials over Q, then we can find suitable n1 and n2 from Z such that both n1 Gx and n2 Hx will be polynomials over Z. Consider g1 x equal to n1 into Gx and h1 x equal to n2 into hx, and n equal to n1 into n2. Then fx equal to gx into hx implies that n fx equal to g1x into h1x. Actually, we will cancel n from the left part step by step using their prime factors. Suppose p is a prime factor of n, then the identity n fx equal to g1x into h1x becomes g1x into h1x bar equal to 0 over Zp. Since Zp is an integral domain, Zpx is also an integral domain, and then the product g1x bar into h1x bar equal to 0 implies that at least one of g1x bar and h1x bar is 0. We assume that g1x bar is 0. Hence, p divides all the coefficients of g1x. So, g1x can be rearranged as p into g2x for some polynomial g2 over z. Since p is a prime factor of n, we also have some m such that n equal to pm. Then n fx equal to g1x into h1x implies that fx equal to p g2x into h1x, which again implies that m fx equal to g2x into h1x. Thus, which I have already mentioned that we will cancel the integral coefficient of f in the left hand side by cancelling their prime factors step by step. We have already performed our first step, and continuing in this way, all the prime factors can be cancelled and we will reach our desired factorization f x equal to g x into h x in z x. Though we see that the proof of the Gauss lemma is simple one, still it plays a fundamental role to characterize irreducibility of polynomials over the field of all rationals. Here we will use the Gauss lemma to prove two results on the irreducibility of polynomials over Q. In the first one, we will reduce a polynomial over Q first to a polynomial over Z and then to a polynomial over ZP for some suitable prime P. Let us see how. Suppose f x is a polynomial over Z and degree of f x is n. Then we will associate a polynomial f bar x to f in such a way that degree of f bar x is equal to degree of f x, and we will have to choose a suitable prime P so that f bar x becomes irreducible over ZP. The efficiency of this result is in the fact that ZP contains only finitely many elements. So, if we consider a polynomial f x of degree 2 or 3, then the irreducibility of f bar x can be checked easily. Okay. Let us start the proof. Suppose that P is a prime such that degree of f bar x is equal to the degree of f x and f bar x is irreducible over ZP. We are to prove that f x is also irreducible over Q. If not, suppose that f x is reducible over Q. Though this is reducible over Q, Gauss lemma gives us that there are polynomials g x and h x such that f x can be expressed as a product of g x and h x, and g x and h x can be taken from z x. Since degree of f bar x is n, it follows that product of b k and c l is non-zero in Z P, and hence b k is non-zero and c l is non-zero. Consequently, g bar x and h bar x are non-constant polynomials in Z P x. This implies that g bar x and h bar x are non-units. Since the non-zero elements of Z P are the only units in Z P x, hence f bar x is reducible over Z P, but we assumed that f bar x is irreducible over Z P. Thus, this is a contradiction, and this contradiction arises because of our assumption that f x is reducible over Z. Thus, it follows that f x must be irreducible over Q. Let us demonstrate an application of this result. Suppose f x equal to 7 x cube plus 8 x plus 2 over Q. We are to choose a suitable prime number P so that the associated polynomial f bar x is a polynomial of degree 3. Consider P equal to 3, then note that f bar x becomes x cube plus 2x plus 2, and also note that f bar has no root in Z3, and since this is a polynomial of degree 3, it follows that f bar x is irreducible over Z3, and hence f x is irreducible over Q. Now, we will prove the great Eisenstein's criterion on irreducibility of polynomials over Q. Suppose f x is a polynomial over Z. Condition says that if we have a prime integer p such that p divides a0, a1 up to a n minus 1, p does not divide a n and p square does not divide a0, then f x is irreducible over Q. Here also we prove the result by the reductio ad absurdum. Assume on the contrary that f x is reducible over Q. Then by Gauss lemma we have a factorization f x equal to a polynomial having coefficients bi and a polynomial having coefficients ci over Z. Denote the first polynomial as gx and the second as hx. Then f x equal to gx and hx implies that f bar x equal to gx bar into hx bar in zpx. Since p divides a0, a1 up to a n minus 1, so f bar x becomes a box a n into x to the power n, and since p does not divide a n, so a n bar is a unit in Zp. Now, p divides a I for I equal to 0 to n minus 1 implies that f bar x equal to u into x to the power n. Since irreducible factorization of polynomials over a field is unique, so we have g bar x equal to v into x to the power k and h bar x equal to w into x to the power m, where u v are units in Zp. Thus, it follows that b0 bar equal to 0 equal to c0 bar in Zp, that is p divides both b0 and c0, and it follows that p square divides a0. This is a contradiction to our hypothesis. Hence, our assumption that f x is reducible is wrong. Thus, it follows that f x is irreducible in Qx. Consider f x equal to x to the power 5 plus 12 x to the power 4 plus 9 x square plus 6. If we take the prime p to be 3, then all the hypotheses of Eisenstein's irreducible criterion are satisfied, and hence f x becomes irreducible over Q. Now, we show that the pth cyclotomic polynomial, which is phi p x equal to 1 plus x plus x to the power p minus 1 is irreducible over Q. Here actually we will prove that phi p x plus 1 is irreducible over Q, and eventually it will follow that phi p x is irreducible over Q. Note that phi p x plus 1 becomes x to the power p minus 1 plus p c 1 x to the power p minus 2 and so on, and the constant term becomes p c p minus 1, which is actually p. Since p is prime, we have p divides all these coefficients, that is p c 1, p c 2 and p c p minus 1, and hence by the Eisenstein's irreducibility criterion, it follows that phi p x plus 1 is irreducible over Q, and the result follows. Now, we will discuss on an application of the irreducible polynomials to construct finite fields. Most known example of finite fields are ZP, where characteristic of this field is a prime P, as well as the field contains prime number of elements. Here we show that there are finite fields, though their characteristic is a prime, but may contain elements of non-prime numbers. For example, we can construct finite fields of 4 elements, may construct finite fields of 8 elements, may construct finite fields of 9 elements, and so on. To give examples to construct finite fields, first we prove the following result. In this theorem, the following 3 conditions are equivalent. Suppose f is a field and Px is a non-zero polynomial over f. Then irreducibility of Px is equivalent to the fact that the quotient ring Fx by ideal generated by Px is a field. We will use this theorem to construct finite fields having non-prime number of elements. The details of the proof can be found in the e-content. Here I give only the basic idea. Actually, if Px is irreducible, then for any polynomial Fx which is not in the ideal generated by Px, in other words, if Fx plus ideal generated by Px is a non-zero element in the quotient ring Fx by ideal generated by Px, then Px does not divide Fx, and which implies that GCD of Px and Fx is 1, that is they are relatively prime, and which with the help of Bezout's identity implies that the element, the non-zero element Fx plus ideal generated by Px has a multiplicative inverse Ux plus ideal generated by Px in the quotient ring Fx by ideal generated by Px. And since the polynomial ring Fx is already qualified to be a commutative ring with unity, so is the quotient, and now we have shown that every non-zero element is a unit. Thus, it follows that the quotient ring Fx by ideal generated by Px is a field. The rest you can find in the e-content. Now, we give an example to construct a finite field. Consider the irreducible polynomial Fx equal to x square plus x plus 1 over z2. Then by the previous theorem, it follows that the quotient ring F is a field. Now we show that F contains only 4 elements, and we will show this with the help of division algorithm. If we use division algorithm, then we get unique polynomials Qx and Rx satisfying f x equal to x square plus x plus 1 into q x plus r x, where either r x equal to 0 or degree of r x is less than 2. So, whatever it may be the case, r x must be of the form a x plus b, where a and b are in Z2. Since Z2 contains only two elements 0 and 1, so a and b can be chosen together in 4 ways, and thus these 4 polynomials r x will give 4 distinct elements of the quotient ring F, and these 4 elements are 0 plus ideal generated by x square plus x plus 1, which corresponds to a equal to 0 and b equal to 0. If we take a equal to 0 and b equal to 1, we give the second element, which is actually the unity in this field, that is 1 plus ideal generated by x square plus x plus 1. Similarly, we have other two elements, namely x plus ideal generated by x square plus x plus 1 and x plus 1 plus ideal generated by x square plus x plus 1. Thus, this is a field having 4 elements. Here I wish to mention that these finite fields are very important in the theory of cryptography, in Galois theory, etc. We will discuss again in our Galois theory modules. These are all 4 modules on the polynomial rings. In this chapter, I have given a special emphasis on the polynomials over fields. Actually, in our postgraduate course content, we will apply again and again the results on polynomials over fields. Here we have discussed division algorithm, irreducibility of polynomials, and proved that every non-constant polynomial can be expressed uniquely as a product of irreducible polynomials, and in the final module we have proved some results to test irreducibility of polynomials and demonstrated an example and application of the irreducible polynomials to construct finite fields having non-prime number of elements.